My name is Tyler Steffen, and this is my applied machine learning project, predicting the time evolution of wave functions with UNets. The essence of the problem is that we have some complex valued field psi that we want to compute at some future time step dt away. This is governed by the Schrodinger equation, which is given over here in these two forms. This is a really basic form that just shows this is how we compute something at a future time step. And this is the form that really highlights what the time-wise derivative is. So the time-wise derivative consists of two major components, which is the potential component here, which is sort of cleverly ignored for the purposes of this computation with boundary conditions. And then the more computationally intensive part here, which is the Laplacian. The Laplacian requires us to compute finite differences at every point inside of the field, which is very computationally intensive. So the goal here is to really replace this version of the update of the field with some sort of forward convolution of the network. And hopefully this will be much more energy efficient and a lot quicker. Physics-informed machine learning is a big field, not only in academia, but also in commercial aspects. There's a lot being invested in places like NVIDIA. The biggest source of information for me, though, has been Steve Brunton at the University of Washington. He has an ongoing series releasing on YouTube about physics-informed machine learning, a lot of prediction and digital twin-oriented things, and I've found it extraordinarily interesting and extraordinarily helpful. Him and his colleagues also publish very regularly and have a lot of heavily related material on stuff like fluid mechanics and partial differential equations, and even the Schrodinger equation itself. So there is existing work. The one area that I've seen kind of lacking is time evolution of multidimensional wave equations. I have seen a lot of fluid mechanics simulations, but particularly wave equations with neural networks and especially UNets I have not seen. So it's something that I wanted to investigate more. So the general process started with the generation of data. I couldn't find any good data sets on wave functions that existed that would suit my needs, so I had to generate them myself. And that started by me creating a Python package, which I have titled Cython. It is now publicly available, and its main purpose is just to simulate wave functions really flexibly inside of PyTorch on a wide variety of hardware. So my first training set was 10 sims, and these were randomized particles in randomized locations with randomized wave vectors k, and the wave vector dictates the momentum of the particle. Each of these took very consistently 3 hours, running at 200 to 220 watts on a 4090, so these are not computationally cheap. They push the 4090 to its limit. The simulations were ran at a resolution of 1000 by 1000. I can run them at higher resolutions, but they would take much, much, much longer. So you have to compute these at very small time steps, as I mentioned earlier. So these were 30 million time steps, and only 1 in every 50,000 frames was actually rendered out. And so this results in 600 frames, and then that can be rendered to whatever sort of video that you really need it to. And these were saved in HDF5 files. This is a really general representation of what the computation looks like. And it just kind of shows how computationally complex it is, having to run at every point inside of your n-dimensional field. Next, I'll get in a bit more to the actual model and how I brought that all together. One of the biggest things that I did was I made a custom dataset class, which helped me bring in a lot of datasets for training at one time, but also still maintained that the next step was actually still the next step from the same dataset, and that it was properly training in time, such that I wasn't pulling from two different data sets, say the last frame of one data set and the first frame of the next, and saying that's the next data or the next frame in the same data set. This is the basic definition of the UNet here, which can be visualized right here. This is created with TorchViz, and you can see the basic U shape of it. It's a bit too intricate to really dive into though. This is the training loop. I used, as I think I stated earlier, mean square error and Atom. Mean square error is definitely pretty naive for this purpose. It works, but I think there's a lot that can be improved with the error function that would yield a much more physically coherent model. And I'll get into that more later. Training is very expensive. It really throttles both the CPU and the GPU. There's a lot of data that needs to be loaded, and it requires a very substantial system. Bringing in all the data sets together totals up almost 70 gigabytes because each data set is 6.7 gigabytes. So it requires a substantial machine to be able to even train. Now getting into some of the results a bit. So I'll just let this play for a second. On the left is the classical method, the original simulation method that was used to generate the data set. And on the right is the simulation that was generated with the UNet. I'll play it again, but probably the biggest thing to look at here is the power and the speed at which this was able to happen. So the UNet was able to generate this in less than half a minute, while this took the classical GPU method 3 hours to generate. And yes, the UNet used more power instantaneously, but overall that's a lot less energy consumption. Generally, in terms of the results, I think it's important to see that yes, the UNet model completely decoheres and loses its wave, like any semblance of single wave packets, but they still do approach what are somewhat similar final states, and the entropy trends are very similar. On top of that, you can see, at least in the early parts of the UNet simulation, that the wave mechanics are like progressing how they should, in the sense that the waves in the complex and real fields are causing progression of the actual absolute field forward in some direction, associated with the wave vector k. So the Fourier transform of the position domain of a wave function equates to its momentum domain. So these sinusoidal curves that are seen inside of the wave function dictate its momentum and cause it to propagate. So there still is some of that propagation being obviously observed in line with the sinusoidal portions of the wave function, which is not, this is all trained on large data sets. So the fact that any of this is getting through to the UNet is very promising to me. And just generally, I am still very, very happy with the fact that it's able to simulate that so quickly. So just going over a couple other things with the results that I sort of already covered, but it's really nice that the entropy trends so match up so well with the original simulations. And it's especially promising because they weren't incorporated in the loss function at all. If they had been, then it would be, oh, I would expect them to. But the fact that they do without even being optimized around it's really encouraging. The one other thing I noticed is that the UNet approaches the sort of chaotic state of the simulation much more quickly. So my thought is that because maybe large portions of the original simulations were chaotic and this was the input training data, that's sort of dominant, and the UNet has no real time way to recognize where it is in the simulation. So adding in more parameters such as entropy would help better describe to the UNet how it needs to progress the simulation at the current state, such that it doesn't jump to the more chaotic states of the simulation. All right, so concluding and looking forward, I'm really, really happy with the results I have just with such a general model. I have a couple areas that I want to look at improving. Like I've already stated, the loss functions really need to be looked at. There's a lot of different ways that this can be augmented with, as I've said, entropy, energy conservation needs to be looked at. There's plenty of symmetries in quantum mechanics that can be implemented. And looking at the spectral domains, just taking the Fourier transform and making sure that stays in line. I think those are all good implementations of losses that could be added. Um, and then more directly enforcing some of those aspects through the architecture itself. Different filter layers can be incorporated to almost freely enforce things like hermeticity and certain symmetries. So I think that's really, really worth looking at, and I will be doing. Now onto a quick tour of the code. So everything is built inside of, as I've mentioned, my package Python. This is the basic building block of everything. It's a field, and the most important object here is probably the tensor, which is a complex valued tensor. It just has a lot of functionality for doing physics sort of things like adding in a wave packet and calculating the entropy of said field, and then making the update with the Laplacian. Then there's just input and output functionality here. These are put together in a universe class. So universes have fields, and then universes have simulation functions. So there's no real interaction between the fields currently. That is something that I'm going to work towards in the future. But currently, fields just sort of simulate independently of each other. And this is the main sort of simulation loop. So this is the classic method that we're trying to replace. This is a simulation class that I've used to sort of bridge between my classical simulation methods and the neural network methods. So it just holds fields in it. Most of the time I've been loading in simulations from an HDF5 file, which is how I save out the simulations from the classical models. And then it just has some functionality to save out to videos and plot entropies and such. Now onto the model. It was also up over here. I guess I'll just pull up the UNet model though. So that's the real chunk of it. It's a very regular UNet. The only thing is that it has options for channels, which are just used to, I always use two channels, one for real and one for the imaginary. So it's a very basic UNet, other than it has the option for extra floating point channels, and the complex number is just split. There's probably better ways to do this to enforce the relation between the complex and real components of the wave function, but this is producing some results, and it's a basis to improve on. And then here's the training loop. So using this dataset class right here, I also have a single dataset class, but it's kind of useless considering the multiple dataset class. I load in simulations that I have on the network drive. They sit in RAM, like I said, 70 gigs in RAM of all those, and then it loops through all of them. And this simulation, in this training set, I did 20 times, but it had stopped optimizing after about 10 or so. And just like I said, basic MSE and Atom. Nothing really interesting there yet, but I'd like to improve on that a lot in the future. And then finally, this is the model being loaded back in, and then I open up a simulation from the classical model, and I take the first time step from that and use it as the initial step of the simulation with the UNet. So after I load in that first time step right here, I just iterate through and use the UNet as the forward. So right there, you can see the current time step is used as the output, and then it's printed out to the terminal. And just to finish everything off, we can run a simulation. All right, and there's our simulation, chugging ahead with the UNet. Thank you very much. This has been my presentation. Let me know if you have any questions. Everything should be available on GitHub. Thank you.